Hello everyone and welcome to this lecture. In this lecture, we will start a new topic and this topic is very famous. The topic is about random walks on graphs. Okay, it has application is Google PageRank, in finance, and there are many other applications. It's an example of Markov chains. Okay, I will shortly tell what these are. And so what is a random walk on graph? Okay, it is kind of a walk what a drunkard will follow. Okay, so suppose he is at some vertex, right, or some location in graph, right, and of course there are suppose 3-4 adjacent places to it, right, which are directly connected. Basically it has edge, that the current position has edge to these maybe 3 or 4 positions, and out of those 3 or 4 positions the drunkard will randomly select, right, and at every position after going to that position it will again choose the same way, right, randomly choose its neighbors and keep on going. Such a walk we call random walk. So let me just pictorially tell you what exactly this means. Okay, so suppose this is a graph, right, and at some point suppose the random walker has started or drunkard has started, and after some time, suppose at time t it is at some vertex u, okay, at time t. Okay, now suppose this u has maybe these many neighbors. Okay, in the next step this random walker will choose either of these, right, so let me call it vertex 1, 2, 3, 4, 5, okay, and it will choose randomly, right, it will choose randomly to which location he or she will go. Okay, so what is the, suppose I ask you what is the probability at t plus 1 step, the random walker or the drunkard will be at node 5. The probability is here how much? 1 by 6, because there are 6 ways, 6 options for your drunkard, and he or she is choosing it randomly. Okay, choosing a location or a neighbor randomly. So the probability here is 1 by 6. Very good. So now suppose this random walker had started at some vertex. I mean, maybe you can call p at time 0, at t equal to 0, and then she is following this, and then maybe after some time he is reaching this. Okay, and then after so at t time he is reaching at u, and then after t plus 1 step we want to know at which vertex it will be. So we want to know the probability at which vertex it will be. So for example, probability of the random walk being at 5 is 1 by 6. Similarly for 3 and 4 it is 1 by 6. Okay, so how can we, so what is and I told you in the beginning that this is kind of a Markov chain property. Markov chain is what? It is actually the phenomena where your current position, only the current position will determine your future position. Okay, so basically if you see here, it doesn't matter how you reached at u, but if suppose it is given that somehow you reach at u, so basically at t time that you are at u, okay, your next position at basically at t plus 1 position, right, just depends upon u. Okay, it doesn't matter how you reach to u before t steps. Okay, so and then you really want to, I mean, this is very obvious, right? There are many things which are not Markov chains. For example, if I tell you about throwing a ball, okay, so suppose some ball is in the space at t time, suppose the ball is at here, right, what will be the next position of ball? Okay, it only depends upon this position. Suppose this is some position and this ball is here, there's the next position at t plus 1, suppose, okay, will only depend upon the position at t. Okay, suppose the next position is here, but this next position only depends upon the position at t? No, it actually depends upon the previous position. So suppose the trajectory of ball is this, so maybe the next position will be this, but suppose the trajectory of the ball was this, maybe the next position was this one, right? So the previous positions are also required here, previous to determine what will be at t plus 1. But for here, if we know that the ball was at time t at u, you can tell the probability that what will be the next probability of random walker, or or basically drunkard here, at which point it will be. You can tell just by knowing that at t time it was at u. Okay, so very good. So now let us move to so we will be asking 2-3 questions here. Okay, one thing is, suppose this random walker is keep on going and going after starting at some vertex, right? What is the probability that after longer time that random walker or drunkard will be at some vertex? Okay, in fact we want to know for all the vertices, okay, what is the probability that, oh, the random walker will be at vertex 1, what is the probability that, oh, the random walker will be at vertex 2, and so on after long time. Such we call limiting probability. Can we always determine this? Can we always determine, basically, is this probability converge? Okay, or are they fluctuating? Maybe after very long time, maybe for some graphs we cannot determine the exact probability. Oh, that the probability of being at that vertex after long time will be this. Maybe we cannot determine it. Okay, so in this lecture, in fact this lecture onwards, we will determine this beautiful phenomena that there are graphs for which you can always tell that after sufficiently longer time what will be the probability that the random walker will be at given vertex. Okay, so this is very, and more interesting that it doesn't matter from where the drunkard started or basically the random walker started. Okay, so these two things are very interesting here. And the last thing that we will prove, how fast. So suppose the probability after some time becomes constant, right? But how fast we are achieving that? In how many steps we can achieve that? So there are 2-3 very interesting questions lying ahead. So let me first develop some formal notations and all. And okay, so so like in the pictorially I have told you. So suppose I want to know what is the probability that at t plus 1 the random walker is at vertex v, some vertex v. If you see it carefully, so suppose this is vertex v, like here, no, not here, but here. So we want to, we can easily tell if, so we want at t plus 1, right? What is the probability that the random walker is at v at t plus 1? All I need to know is whether at t time the random walker whether the random walker was at some of its neighbors, right? So maybe so these are its neighbors, right? Suppose this. So was the random walker at t time was here or here or here or here? With what probability the random walker was here? With what probability the random walker was here? With what probability this random walker? So basically it's a sum over all the probabilities, and then random walker is taking a step to v from these neighbors. Okay, so this can be written as summation over all the neighbors of, so let me denote it by the all neighbors u or v, and then what was the probability that the random walker at t time was at u, at u. Okay, and then what is the probability that the random at t time the random walker was at u? What is the probability that in t plus 1 it will take the step to v, right? And this probability is nothing but 1 divided by the number of, suppose it is u, the number of edges incident to it. Basically it can, so u at t time was here, at t plus 1 it can take this edge, this edge, this edge, and this edge. So there are 5 edges, so it can take any one of them randomly. So the probability of that will be 1 by 5, right? So this will be nothing but degree of u, right? Number of edges incident on u. So this is nothing but degree of u. Okay. Now, actually I want some more generalization to it. Okay. For this lecture, in fact, for next maybe 2-3 lectures, till this random walk things will be going on, I want this graph to be basically weighted graph. Suppose there is weights on edges. Suppose here, so suppose this weight is w, or actually I will denote with this weight by m uv. I will tell you the region because I will be using this WB for other thing. Okay, suppose this is, let me write it clearly. Suppose this is edge UB, so I will denote the weight on UB by B, and this weight is actually, so graph is still undirected, so weight will be, this will be following, and let us assume that these weights are non-negative. If the weights are 0, that means there is no edge, otherwise you assume that there are positive weights, right? So when there are positive weights, so what will be, how can I modify this? How can I modify this equation? In that case, what I will do, the probability of moving from U to V will depend upon the weight of the edges, the edge of U and V, which is connecting U and V, right? So that edge. So basically, now I will write this edge. Let me first, for generalized case, generalized case. Basically, the weighted graph, weighted undirected. More the weight of edge, more preference it, will be given to it. So more probability will be of that choosing edge, right? Undirected, weighted undirected. Okay. Edges. Very good. So how I can actually modify this? In that case, this will be nothing but PT plus 1. V is nothing but, again the same thing. There is some, again the same thing. So P, sorry. Summation over all the neighbors. Okay. Then let me denote this weight by, suppose the probability of at T was U. Then from U it will move to V, right? With how much probability? The probability will be given by UV divided by total weights of edges at U. So this I will denote again by U, and let me write what by DU means. So DU is nothing but, you may call that, so summation over, suppose all the neighbors of U. So suppose this is W, and then you are adding all the weights of basically UW. Very good. So this is degree, or you can call weighted degree. So weighted degree of U. Very good. Now this was about V. How can we write for all the vertices? Basically, how can I write a probability vector? So basically this, what is the probability at T plus 1? The random walker will be at 1, 2 and so on, right? So basically the vertex 1, 2, so this was at V and so on, vertex. I want to know this vector. How can I write this vector in terms of, basically I want to write something in terms of matrices and vectors. Okay, so if you see it carefully here, if you see it, this fact is beautifully captured in a matrix product. Okay, so let me first write a weighted matrix. This matrix is nothing but, so M11, M12 up to M1n and so on. So let me write, okay, so this will work. So M and 1, M and 2, M and n. Okay, and suppose at some time this is V, right? So let me write, so V, M, V1, M, V2 and so on, M, Vn. Right, now remember, just focus on this, how we are making this entry. So this is nothing but summation over all the neighbors of V. Okay, and then from that neighbor it is jumping to this with some probability, right? Now suppose these are again the same thing, vertex 1, vertex 2, but suppose this is the situation at time t, the probability vector at time t. So probability of being at 1, probability of being at 2, probability of being at n at time t. Okay, now what it will do, so if we want to find this is nothing but, oh, what was the probability at time t that the random walker is at vertex 1, and is there an edge between 1 and V? If there is, and what is its weight, and then you divide the weight of that degree 1 by its weighted degree, right? So this will be nothing but, if you do, so I can divide by degree of 1, then degree of 2 and so on, degree of 2, right? No, degree of n, it will be degree of n, right? Sorry. So let me clearly write it. degree of n, and summation over all this will give you actually Vt. So basically dot product of this vector times this will give you the probability of the random walker being at V at time t plus 1. Very good. So I can actually, now this is for basically everyone. So right, basically what is happening, I will divide each column by first column by d1, second column by d2, and last column by dn, and then you multiply with pt, right? And this will give you the pt plus 1. Okay, so in matrix term I can write this. Suppose this is matrix, so this weighted matrix, suppose I write with m ub or mij, right, ijth entry, and this degree matrix, suppose I write with this. So degree matrix is this. So weighted degree of first, weighted degree of second, and weighted degree of the last one. Okay, so I can, this setup I can write this as, so pt plus 1 I can write as m d inverse pt. Very simple. Okay, so please keep this notation in mind. Okay, and let me denote this matrix in fact by w. So this will be maybe more, I will let me, okay, so let me say this is equal to w pt, where, so let me write outside this, so w is equal to md inverse, or that means, because d inverse we are taking connected graph. Okay, so d will be always non-singular. Okay, and so I can write again. Very good. Now before moving, so we will see that by the eigenvectors of w and eigenvalues of this w, we can actually determine after after many steps, what will be the pt plus 1, or what will be the probability that the random walker will be at some vertex. Okay, and this probability is after some time actually becomes constant. Very beautiful legend, and in fact doesn't matter from where we started. Okay, memoryless thing. Okay, so but before that, analyzing w, let me make this slightly more generalized. Okay, have some patience. In fact, there is something more beautiful thing coming up that we call something lazy random walk. Okay, so lazy random walk, let me tell you what it is. Now suppose your drunkard is lazy person. Okay, at a given position, at a given point, right, he or she want to stay at the same position with some probability. Okay, and he want to move to rest of this, right, with probability 1 minus that probability by which he is staying on the current position. Okay, in that case basically how can we write? So suppose alpha is the probability with which he want to be stay at the, wherever he is, he want to stay at this position, right, at with probability alpha. So in that setup I can write this probability at being at v at t plus 1 is nothing but, suppose he was at v at time t, and then he want to stay at with probability alpha. So with alpha he want to suppose if he was already at time t at v, he want, otherwise now he at some other position, now with 1 minus alpha he want to jump to v, right? So this will be nothing but this. Now you do the same thing here that we have done it. So basically summation over all the neighbors of u, then m u v, okay, and then degree of u, and at time t the random walker was at u. Very simple one. And matrix, how can we actually write this expression in terms of matrix? So this will be nothing but very simple, that pt plus 1 in this setup will be alpha times I plus 1 minus alpha times this md inverse, or maybe md inverse I have already told you that this is equal to w, so I can safely write this as w. Very good. So this will be your probability vector at t plus 1 in terms of pt. Okay, now further let me call this matrix as w, this matrix as W tilde. So there will be slight notations, and please do not confuse with this. I am a very simple one. So I can in fact write this PT plus 1 as W tilde PT. Okay. Now like I mentioned here, I want to know the eigenvectors of W in the first case. Now I want to know the eigenvectors of W tilde, and they beautifully tell you what will be the limiting probability. How can we determine the probability that random walker will be at some vertex at time t plus 1 after sufficiently longer time? Very good. So now let us start with analysis of eigenvalues and eigenvectors of W. Okay, analysis of eigenvectors and eigenvalues of W or W tilde. One thing is that W tilde, or in fact W, may not be symmetric matrix, right? They may not be symmetric matrix because we have multiplied with D inverse, right? So this may not be symmetric. But one thing is also sure, that if we know the eigenvalues of W, we know the eigenvalues of W tilde. It's nothing but alpha plus, and you multiply with 1 minus alpha to the eigenvalues of W. So very simple. Okay. So now, but how to, does eigenvalues of W or W tilde are real? Remember, these are not symmetric matrices. Okay. But are they real? Okay. In fact, if you see, we will prove that these are real eigenvalues by showing that these eigenvalues are actually equal to, basically eigenvalues of W are actually equal to eigenvalues of some other matrix, which is symmetric matrix. Let me tell you what is that symmetric matrix. So suppose A is nothing but a normalized weighted matrix. Normalized, so remember, M was your weighted matrix, and suppose you to every entry of your this weighted matrix, suppose you divided by degree of I and degree of J, right? So you see that then this matrix we will call at weighted matrix, and this becomes symmetric. So A will, so this is nothing but dividing here by D half, here by D minus half, sorry. So this is a symmetric matrix. Now this becomes a symmetric matrix. We will prove that claim is the eigenvalues of what A and W are same. That means, but the eigenvalues of A will be real, right? Because A is symmetric matrix, and W will also have the same eigenvalues. So W's eigenvalues will also be there. Let us prove this very nice fact. Proof. Suppose Ax equal to lambda x. Basically, x is eigenvector of A and lambda is its eigenvalue. Okay. What about W? Remember, can I write this equation? Remember, AD, if I write D half, A equal to, yes, correct, MD minus, this is correct, right? So this will implies that, and how can I write MHW, right? Now remember, M was WD, very good. So I can write from that M was WD, so this will be WD minus half. So this will be WD half, very beautiful. Now what? Now do Ax is equal to lambda. You multiply both hand side by x. So basically now this will imply further that D half Ax equal to D half x, right? Very good. Now I know that Ax is equal to lambda x. Okay, so which in fact implies that, so this is equal to lambda x. So I can write this as D half lambda I can take outside. Wow. So you see that this is a vector, eigenvector for lambda. So W has eigenvalue lambda with eigenvector d. Very good. In fact, we have got they have the same eigenvalue. W and A have the same eigenvalues. Okay, and the eigenvectors we know, if x is eigenvector of A, then corresponding eigenvalue vector will be d to the power half into x. Very simple. Now, before ending this session, actually these are pretty much the preliminary for our interesting result that will prove that that the probability becomes constant after some time, but not for all the graphs. We will see for what kind of graph this is done. Okay, but before ending this lecture, I want to know what will be some eigenvalues of W. Okay, let us try to find some eigenvalue of W. If you see that W, we can write again, W was what? MD inverse, right? My W eigenvalues of W, that means eigenvalues of A, right? Eigenvalues of A, eigenvalues of W. Okay, remember W was what? MD inverse, right? If we do this, suppose D is your degree vector, weighted degree vector, D1, D2, Dn. These are weighted degrees, yeah? Weighted degrees. Very good. So what you will do is this. Suppose if you do this, now remember this quantity is what? You are again divided by D1, D2, right? So it will be all one. So this will be nothing but all one vector. Okay, but what is this? If you are so all one vector, basically what it will give, it will actually add all these rows, and if you add the rows, basically you are adding all the vectors. So again it is giving the degrees. So basically it is giving D. So that means D is an eigenvector. D is an eigenvector of D is an eigenvector of W with eigenvalue or corresponding eigenvalue as 1. Very good. Now before ending this lecture, I want to give you a DIY. DIY is this: prove that the eigenvalues of W lies between are in this set -1 to 1. Okay, they cannot be beyond this, from 1 to minus. Okay, so thank you very much, and lot of interesting things are ahead of us. Okay, so see you in the next lecture. Thank you very much.